So hello friends, welcome to the today's lecture of here we will discuss the classical Fredholm theory for solving Fredholm integral equation of second kind. So basically we are looking at this kind of solution, that suppose we have this Fredholm integral equation of this kind, yx equal to f of x plus lambda times a to b k of xt yt and dt. So in a previous lecture we have seen that if this k of xt is of separable type, that summation I equal to 1 to n ai x bi t, then we can write down the solution as y of x equal to f of x plus lambda times a to b gamma x t lambda and f of s d of s, here f of t dt. Here I am using t, so it is f of t and dt. So here f of t and dt, and we also have seen that we can write this gamma x t lambda, the resolvent kernel, as ratio of two polynomial in terms of dxt lambda divided by d lambda, and this expression valid in a region say modulus of lambda less than or equal to b inverse, and provided that d lambda is not equal to 0. So in this case the solution is unique, and you can get by evaluating this resolvent kernel gamma x t lambda, and this we have seen. Now what we want to do in today's lecture is generalize this theory for any given kernel. So it means that here we are assuming that this f of x and kxt are L2 functions, and then we try to find out, then can we write the solution of this Fredholm integral equation of second kind as this kind of thing, where your gamma x t lambda can be written as ratio of two functions dxt lambda upon d lambda, where d lambda and dxt lambda we can find out later on. So to start with, let us look at this method which is proposed by Fredholm himself, and he he gave three theorems known as Fredholm first theorem, second theorem and third theorem, which gives the solutions for all lambdas, and it is as follows. So just look at here, what he did is to solve this particular equation, what he tried to do, he is try to discretize this integral into finite summation. For this what he did, he simply divide this interval a to b into n equal number of parts. So here let us assume that we have x1 equal to t1 as a, and x2 equal to t2 equal to a plus h, and so on, or you can say you can take h as b minus a by n, and using this I can simply say that this kxt yt dt can be written as this finite sum h times I equal to 1 to n kx xi y of xi. Now using this discretization, using this writing integral into this finite sum, we can write this as that equation 1, this y of x equal to f of x plus lambda integral here can be written as y of x equal is approximately equal to f of x plus lambda h I equal to 1 to n kx xj y xj. Now this expression is valid for all x in terms of a to b. So what to do here, you let us consider this equation at x equal to your xi's. So how we have defined xi is defined like this: x1 as a, x2 as a plus h, xn as a plus n minus 1 h. So looking at this equation at x equal to xi, we can write down as y of xj is approximately equal to f of xj plus lambda h I equal to 1 to n k xj xi y xi. Now here this will give you this will give us the solution of this integral equation, approximate solution at the point say x1 to xn. So it is not giving all the solution for entire x, but it is giving the solution, or you can say it interpolates the solution at x1 to xn. So it means that the solution obtained by 17 is the interpolation, or it is the approximation of the solution at endpoints x1 to xn. Is it okay? So let us try to find out the solution here. So to solve this, let us simplify the notation here. Let us write down yxj as yj, fxj as f of j, and kxj xi you write it kji, and using this simplified notation we can write this equation as integral as an algebraic equation, right. So this I can write as yj minus lambda hi equal to 1 to n, kji yi equal to f of j. So here if we can solve this, we can get the solution yj here. So it means that you can get the solution of the integral equation at particular points x1 to xn. To get this, this you can solve in terms of you can write it this as d lambda matrix d lambda yi. You can write it like this. So here we have yj minus lambda h summation I equal to 1 to n kji and yi equal to f of I, and that is valid for j equal to 1 to say n. So if you write down, you can write down this as like this. So y1 to say yn, and this is your f1 to say fn, and here you can write it 1 minus lambda h k11 minus lambda h k12 and so on, minus lambda h k1n and so on. Here you can write minus lambda h kn1 to 1 minus lambda h knn. So if you remember, the similar kind of expression we have discussed for separable equation. The only thing is that there k11 is replaced by a11 and so on. So we can say that if we denote this as d of lambda, determinant of this is denoted as d lambda, then the solution y1 to yn is depending on d lambda, or you can say that in that case you can write down solution yi as say your d I lambda divided by d lambda. I can write this as d, yeah. So d I lambda is, I can further write in terms of d lambda as d I j lambda divided by d lambda. Okay, you can write this as d lambda as this. Okay, so di lambda is the ith column is replaced by f1 to fn. Okay, so this we have seen. So we say that this determinant, if this determinant is non-zero, then we can find out the unique solution y1 to yn in terms of f1 to fn, and if this determinant is 0, then we can find out say approximate eigenvalue corresponding to this system 18. So by taking d n lambda equal to 0, we can get the eigenvalues, and when d n lambda is not equal to 0, in that case we can find out the solution y1 to yn. Now what we try to do here, then let us try to find out the expression of this d lambda. So to find out this d lambda, we try to express this in terms of expansion of in terms of minus lambda h to in powers of minus lambda h. So for that we try to show that the d n lambda can be written as this finite series terms, right. So dn lambda can be written like this. So if you look at, we want to write down dn lambda as this, you can write this as summation, you can write ak lambda minus lambda h power k. So we need to find out what is this ak lambda. K is from 1 to n. So if you remember, we can do we can find out ak lambda as say d upon d lambda k, dk by d lambda k of this capital D lambda, and evaluated at lambda equal to 0. So if we can do this, then you can get ak lambda, but this is a little bit involving. So what we try to do here, rather than writing this, we try to collect the corresponding coefficient here. So what we try to do here, if you look at the constant term is what? If you look at the constant term is nothing but 1, which you can obtain by say multiplying this diagonal term. So here you can say that the constant term is 1, and then we want to find out say the coefficient of minus lambda h here. So here let me write it, what is the coefficient of minus lambda h. So if you look at, we want say power 1 of this minus lambda h. So for that we have to take all the determinant having only one column, right. So for to look at this, let us take a very easy example. Let us take a 2 by 2 example. So here we simply let us take 1 minus lambda h k11 minus lambda h k12, and here we have minus lambda h k21 and 1 minus lambda h k22. And this is, I am just showing that this example 20, you can this expression given in equation number 20 is the correct one. So for that let us take for n equal to 2. For n equal to 1 it is quite obvious. For n equal to 1 it is nothing but 1 minus lambda h k11. So that is quite obvious here. So for n equal to 1 this is quite obvious. For n equal to 2 you can write it like this. So when you expand this, what you will get? 1 minus lambda h k11 into 1 minus lambda h k22 and minus lambda h whole square and k12 k21. So if you simplify this, you can write this as 1 minus lambda h, and it is k11 plus k22 plus lambda square h square, and it is what? It is k11 k22, and here we also have the same thing, minus you can write down this lambda square h square common, you can write this as k12 and k21. So for n equal to 2 we try to show that 20 can be obtained by this. So here I can say that it is 1 minus lambda h, and this is nothing but, say you can write down this as summation I equal to 1 to 2, and you can write it kii plus lambda square h square, and this I can write as you have k11 k12 k21 k22. So this I can write as determinant of this. Okay. So so I am saying that here if I write down this is nothing but, you can say that it is kpp and kpq and kqp and kqq. Here I am just denoting this as something for which p is less than q, right. So here I am writing this as this expression, the value of this when p is less than q. So if I write down a general one, that summation determinant of this kpp, kpq, kqp, kqq, and if we take the summation, then there are two such permutations possible. So I can write this as this second term, I can write it as this summation plus lambda square h square summation here, summation I am taking at PQ from 1 to 2, and if you think there are two such combination, then we have to divide by factorial 2. So if we have two notation P and Q, then there are only two permutation as possible, so you divide by this. Okay, so it means that I can write this term as lambda square h square divided by number of the permutation here, summation PQ from 1 to 2 KPP, KPQ, KQP, KQQ. So for n equal to 2, you can see that equation number 20, or the expression given in terms of 20, is valid. You can also verify that for power in terms of this lambda h cube is given in terms of, say, k, here I am using UU, KUV, KUW, and KVU, KVV, KVW, and KWU, KWV, and KWW. Now again, since we have to take only one, but here we are taking in this, so if we want to take the summation here, then summation over UVW, and such kind of possibility is factorial 3. So we can write that from 1 to 3 here, the coefficient of lambda cube h cube by factorial 3 can be given in terms of this. So this I am writing here as minus lambda h to power cube divided by number of the permutation available, that is factorial 3, UVW from 1 to n, and it is determined like this. So in general you can write that the nth term can be given as minus lambda h to whole power n divided by factorial n, which is the number of permutation available for u1 to un, and k u1 u1, and this kind of determinant k u1 u1, k u1 u2, and so on. So this is the expansion of dn lambda in terms of powers of minus lambda h. So if we take this and use this the short form for this, so here we use this terminology here, that if it is k x1 t1, k x1 t2, k x1 tn. So if you look at in the first row, it is like the first variable is x1, the second variable is vary from t1 to tn, and if you look at the column here, your first variation t1 is the second argument t1 is there, and first argument is from x1 to xn. So if you look at this, this can be summarized as this notation. We are just denoting this determinant by k x1 to xn and t1 to tn. So here what we are trying to write it here we are writing this notation k and x1 to say xn and t1 to tn. Now we are denoting this notation as determinant here k x1. Now you take x1 and then vary for t1 to tn. So x1 t1, k x2 t2, sorry, k x1 t2, and so on, k x1 and tn, right. So first now fix for 2, k x2, and repeat the same procedure. And similarly here we have k xn t1 and k xn tn. So this is the notation we are using, and if we use this notation, then this determinant, which is also known as Fredholm determinant, then in this notation your dn lambda can be simplified as this. So here dn lambda is written as 1 minus lambda h from r equal to 1 to n k xr xr plus minus lambda h to power 2 upon factorial 2 uv from 1 to n k xu xv plus so on, right. So dn lambda is given by this. Now in terms of dn lambda, we try to find out the solution of the Fredholm integral equation of the second kind. So here now if you remember, with the help of this dn lambda you can find out only the values y1 to yn, where y1 to yn is what, y of x1 and it is y of xn. So it means that with the help of dn lambda we are able to find out the solution only the points given here x1 to xn. But if you want to find out the solution at every given point x between a to b, then what to do here, we let us assume that this n is tending to infinity. Now what is this n here? If you remember, n is we have defined as, we have truncated or we have partitioned this ab into n equal part, and we write x1 as say a, and you can write xn as a plus n minus 1 times h, which is given as b. So you can write your h as x minus a, b minus a by I think this we have written as a plus nh. Okay, so here you can say that, let me write it here, a plus nh as b, right. So here we can write this as h as n b minus a by n. Okay, so as n tending to infinity, your h is tending to 0. So in that case we want to show that this dn lambda, this h is tending to 0 and n tending to infinity, then this finite sum is going to go for infinite sum, and we can say that this is going to converge to a limit, first one integral, and similarly this double summation is converted to your double integral and so on. So as n tending to infinity, then as we pointed out that h will tends to 0, and each term of the sum 22 means this is going to convert it into double, triple integral and so on. So if you look at this summation minus lambda h r equal to 1 to n k x r x r, this will go into single integral, and your x r is going to x, and this I can write this as 1 minus lambda k x x d of x plus lambda square by 2 here, and this is reduced to here u is going to x and v is going to some y. So you can write this as double integral k x1 x1 x2 x2 dx1 dx2 and so on. So similarly you can say that as n tending to infinity, that this dn lambda is converted to this infinite series given in terms of this 3. Now here whatever we have discussed, that is just a formal discussion, because we have not discussed the convergence part and so on, because when I say that when you take n tending to infinity, it means that this is going to be infinite series. So I can talk about conversion and all this thing provided I know the convergence part. So it means that I should know that the series which I am writing here is convergent, and then only I can write that the limit n tending to infinity dn lambda, I can write only d lambda. So here if it converges, then only I can write d lambda as this. So here I am not giving the proof here. So we have seen that as n tending to infinity, then this h will tends to 0, and each term of the sum tends to some double, triple integral and so on, and we can say that this one single summation will go to single integral, double summation will go to double integral and so on, because n tending to infinity and this h is tending to 0. So here we can write that the limiting case of dn lambda is given by d lambda, and it is given by 1 minus lambda k xx dx plus lambda square upon factorial 2 double summation k x1 to x2 given in this notation dx1 to dx2 and so on. Now here we assume that the convergence is given. But this Fredholm discussed the convergence part, provided that this kernel kxy is bounded and integrable. So he assumed that if modulus of kxy is less than or equal to m, then the expression this kx1 to say xn, x1 to xn is bounded by m to power n factorial n to power n. So this is given by a theorem known as Hadamard's theorem, and by which we can show that the nth term is bounded by minus 1 to power n lambda to power n upon factorial n, and this integral n times, and this is further bounded by, so its nth term is bounded by this, and you can write this as m to power n to power n by 2 dx1 to dxn, and if you further simplify, it is bounded by minus 1 to power n lambda to power n factorial n here, and this is m to power n, a capital M to power n to power n by 2, and this is nothing but b minus a to power n here. So you can say that this series, your d lambda, modulus of d lambda, is bounded by this summation n is from 0 to infinity, and we can show that this series is convergent, then we can show that this series is also convergent by comparison test. So to show that it is convergent, you simply apply the ratio test and you can prove it. This procedure, including this Hadamard theorem, which says that this is less than or equal to this, is given by a book by W.V. Lovett, and title is linear integral equation. So there you can find out that the convergence of d lambda is discussed, and it is proved that this d lambda converges as an infinite series for all values of lambda. So it is, this convergence is absolute and uniform for all values of lambda. So using this d lambda, now we want to find out the solution y of x at any given point x between a to b for general kernel. The only condition on kernel is that it is bounded and integrable. So if you remember, we have discussed that in case of separable kernel and case of successive approximation, that if we have this kind of equation yx equal to fx plus lambda a to b kx t y t dt, then the solution of this problem can be reduced to in this expression yx equal to f of x plus lambda a to b resolvent kernel gamma xt lambda ft dt, where resolvent kernel gamma xt lambda is given by this ratio dxt lambda divided by d lambda, provided that d lambda is non-zero. So I can we try to find out in next lecture that how we can find out this resolvent kernel and what is the guarantee that it exists, and how to find out this quantity dxt lambda. So this we have already obtained in the case of separable kernel in previous lecture. In this next lecture we are going to say that in this case also for general kernel, how we can find out this dxt lambda and how we can find out this gamma xt lambda, so that we can find out the solution yx given as equation number 25. So we will meet in next lecture to say how to find out this. So thanks for listening us. Thank you.